And get started. My name is Michael Kay from the Department of Industrial and Systems Engineering. And what I want to talk about today is some research that I've been working on really for probably over 15 years. And it's been something that I've really enjoyed because it includes a variety of different things. It's not just a single focus. There's a lot of different elements. And the real goal of the research is to eliminate the need for all non-recreational shopping. So unless you actually enjoy going to the store, it's kind of something that is more of an entertainment value, then that's fine. That will, I think, continue. But for people that do not view it as a recreational event, I'd like to provide the logistics infrastructure that would allow that. And I think it would, in terms of current developments with respect to drones and even some robotic delivery systems that are just starting to be piloted, I think some of the difference of my research focus compared to theirs is that I'm really looking at making the technology so that it allows you to actually eliminate all shopping, so that people that have reasons that they can't go to the store because of disability or whatever other medical or health-related regions that they really can't shop, that they would have access to everything that you would be able to actually get by going to a store. So that changes the focus a little bit from a lot of current work. In terms of looking at the overall cost, one of the goals of the research is to take what is currently really the most expensive piece of the link between actually producing product and then the eventual disposal of the product. The most expensive piece of that is from the store to the house, that last mile delivery. And a lot of different entities, a lot of different companies have identified that as a real opportunity, and there's really been a lot of activity over the last 5 or 6 years in that area. And these are just some numbers that I've put up there to kind of demonstrate what are the potential value of home delivery and why is it generating so much activity. I think because relative to the rest of the supply chain, all of the other links of the supply chain are pretty highly optimized. Essentially everything from when things are produced in the ground, shipped overseas, the Panama Canal is just next month is going to open it with a new wider capability to be able to handle much larger ships, greater numbers of containers. So all that part of logistics has really been highly optimized. Trucking in the United States is very efficient. Even disposal of product, so all the elements are very efficient. I think the one piece that is still missing in terms of really could utilize more extensive research is that last mile effort. And you're starting to see a lot of companies and researchers really working in that area. The overall goal of my research is to really build upon developments in driverless technology. And what's interesting is I remember 10 plus years ago when I would talk about these type of things, where I was kind of focusing my research, I literally had probably a majority of people that would come back and say that not in our lifetime would we ever see driverless technology. That was only 10 years ago. And nowadays it seems like a given. It's happening as we speak. So building on just the basic technology, what I've shown here is what are the economics that would drive this, and using very conservative cost estimates, it basically says that you'd be willing to spend up to $250,000 of investment to be able to replace the cost of one unit. That's what really drives the research, is that having a human involved in that last mile delivery forces a lot of compromises that lead to both inefficiencies and just limitations that the goal of this research are really to overcome. And what I'm proposing is just any type of basic driverless vehicle. And my research is not focused on the vehicle itself, so I'm taking that technology as a given. So I'm not, in terms of actually developing driverless technology, I'm assuming that's happening, and it is happening as we speak. And what I'm focusing on is how would you develop a logistics network that would best support that. So my idea would be, in terms of looking at Raleigh, those blue dots represent small sort of switching stations or distribution centers. So an area like Raleigh, and that red square represents the crossroads area near where I live. And that would show you, hypothetically, how many of these small distribution centers that you could have covering the Raleigh area. And the function of the distribution centers are that it would allow you, if you're at your home, without ever having to leave your home, you'd be able to actually say, today I could order some items from Lowe's Home Improvement Center, and those items then would be shipped from the distribution, from the actual store, Lowe's, to its closest distribution center. And then at that distribution center, the items would then go to another distribution center, to another, and eventually they would reach a point where they're at a distribution center that is closest to the home. And at that point, they wouldn't necessarily have to be immediately delivered. And that's, I think, one of the key points. It's not like a lot of last mile home delivery where you just order it and it's delivered. The idea here is I could order today, but if a lot of the items that you order, you don't need immediately. You maybe need it tomorrow or the next day, or you know that within the next several days I'll probably need this item. So as you make orders, say you make additional orders from Walmart, grocery orders from Kroger, and all of those items would then be accumulating over a 1, 2, maybe 3-day period, and the items would then all be consolidated at this local distribution center. And then finally, when you decide maybe that you want some immediate delivery, and a classic example of that would be like a pizza delivery. If you say I want to have pizza delivered, and say I'm currently at work, say I'm working at NC State, and I'll know I'll be home in 1 hour, well, I can basically arrange to have a pizza delivered within 1 hour, and then within that hour, a vehicle would leave the local distribution center with all of the items that you had previously ordered on board, and then it would stop by the pizza shop, the pizza would be put on board, and then the vehicle itself would then make it to your house. And then you would be there to actually unload the vehicle. So the idea is that you only trigger the delivery when you're available to actually pick up the items. And that's one of the things that using driverless technology makes feasible, because the vehicles are low cost enough and their operating costs are low enough that you can really have the vehicle fit your schedule, as opposed to like UPS or FedEx, where because of the high cost of a human driver, you really have to economize the use of the driver. So the driver just drops it off on your porch and then goes on, and you may or may not be at home. So in this case, it would be delivered only when you actually want it to be delivered. And in terms of the technology, the piece that I've focused on primarily is what would be needed within one of these small distribution centers to actually make it work technologically, what type of material handling devices, and then for the distribution center network itself, how would they interact with other DCs? How would packages be coordinated such that they'd be able to go from one distribution center to another? So one of the key ideas would be that you'd have some type of modular system that would allow fully automated loading and unloading of the vehicles. So the idea of the distribution center is that it's completely lights out. So in terms of the container itself, one possibility for design of such a container would be a small module. The size of this module is about 25 centimeters. And then you would have containers that are in certain modular sizes. And the containers would then go in orthogonal directions, either this way or this way. And the wheels would then pop up or somehow allow the container itself to move in either direction. So with that capability, for example, if you want to be able to access this individual container, well, it's currently blocked, so there's no way of getting access to it. So to unblock it, the other containers would move and allow a path to be made such that this container could be extracted from the storage area. So this is a top view of the size of, I think, a typical distribution center. In terms of just an idea of how big this is relative to anything else, it's about the size of a McDonald's restaurant. So one of the key capabilities of this is that with that small of a footprint, these distribution centers would not have to be relegated to industrial parts of town. They would be able to be located at major intersections. Currently where you have a McDonald's restaurant and a Walgreens, that type of space would be about the footprint that you would be looking for to be able to actually locate one of these. So you have the driverless vehicles that would then arrive at these loading docks and then load and unload their packages. Then this would represent one level or floor of the entire distribution center. So this is a side view of the distribution center. And the level we saw before would be this level right here where the items actually unload directly onto. So this would be sort of a sortation and loading and unloading level. And then you would have conveyors that would carry items to other levels if they needed to be into storage for any length of time. So for example, if I order something today and it arrives at my local distribution center, but I don't actually schedule a delivery till tomorrow, then it could be stored in the intervening time in one of these other levels. So here at the bottom, you have frozen storage, refrigerated, general merchandise. And you could also interface with drone delivery. So if you need immediately something, you could, instead of waiting for the vehicle itself, you could also have drones interact on the roof of this facility. And in terms of the research areas that I'm currently working on, there are basically 4 different areas. One is storage system control. How do you actually operate inside of one of these distribution centers to allow items to be moved around as needed? Second would be design of the actual module itself, those little modules that actually move the containers. A third area is network coordination. How would you develop a mechanism for essentially pricing? What would it cost to actually move items from one DC to another? One of the constraints for network coordination is that I'm not assuming that there's a single corporation or a single entity that controls all of the distribution centers or all of the driverless vehicles. Each one could be separately owned and operated. And the idea of network coordination is to have a mechanism that allows that cooperation to occur without any type of central control. And then finally, the fourth area is performance analysis. And that's basically just trying to estimate what would be expected delivery times and what would be associated cost. In terms of the storage system control itself, the basic idea is you have different levels of control. And at the bottom level, the actual planning and execution stage would be the actual coordination of the movement of the modules themselves. And then the different containers, as they move within the facility, certain of the containers would have different priorities. Something that needs to be delivered very quickly, like once you order something, then you have a fairly short time window where that set of containers needs to be part of the load going to your home. So you would have higher priority than other items that are just waiting to be put away in storage. If they need to wait a little while, it's not going to be as much of an issue. So that second higher level is priority assignment. And then finally at the highest level is load planning and control, and also coordination of the elevators. In terms of path planning itself, the basic approach for this problem that we've used is your basic A-star path planning algorithm. And essentially we were doing really a 3-dimensional version of this problem. And what's interesting is it really relates to a lot of mobile robotics research. And what we found is our problem in some sense is somewhat unique from most existing research. In terms of mobile robotics, a lot of existing research focuses when you have multiple moving robots, you assume essentially a unlimited space for movement. Or when you have a very constrained environment, they focus just on the movement of one vehicle. Our problem is different in that we have a constrained environment, but also we have multiple, not robots, but multiple containers that are all moving simultaneously. So this is the basic problem we have, and you can really think of it as a 3-dimensional path planning problem, where we use different priorities to determine what sequence does each path need to be planned. And then once a path of an existing container has been planned, since it has a higher priority, then the movement of that container essentially becomes an obstacle for all subsequent paths. So they basically have to avoid that. So this would be, here's one example of a set of packages. The ones that are currently on the floor are ones that are already located on the floor. And then you have a series of loads that have been unloaded from 4 different vehicles onto the floor. And then over time, what's happening here is simultaneously all of these containers, their paths have been planned and they're executing. And it's designed so that they're all avoiding each other. So this is essentially a multi-container motion planning problem that's occurring. And as you can see, the movement of the containers are orthogonal, so they either travel left, right, or up or down. And the goal then is to have them all sorted into 4 outgoing loads that can then be sent away by the vehicles themselves. And the numbers on the containers represent priorities. You might think it's almost done, but this is the last one. You see down here, these last 2. Now it's complete. So now these 4 different loads are set, and this load over here is to remain on the floor of the facility. In terms of the module design, this is an area that I've not done extensive research in. I've always really been hoping to find somebody who's really interested in pursuing this. In industrial engineering, we don't have a lot of students that are really terribly interested in this area. They're typically interested in more of the higher level processes. But I've had at least one student who's done some additional work. And one of the, I think, real challenges is that if you build out this entire set of distribution centers and extrapolate, not just for Raleigh, but for the whole country, you'd be talking in the neighborhood of about 2.5 billion modules in 100,000 distribution centers. So in terms of manufacturing cost, you should be able to get the lowest cost possible. If you're going to buy 1 billion of something, then you should get whatever, essentially just what are the costs of manufacturing. So with that, it's, at least in working with students, it's hard to get them to think beyond just current technology in terms of, you can buy these components off the shelf today and it would cost X number of dollars. But I think the real interesting research challenge is to really think a little bit outside the box. Given these very general performance requirements, what can you think of mechanically that would allow that to be implemented? And myself not being a mechanical engineer, I haven't been able to really advance it that far, so I'm hoping to engage the interest of a real clever mechanical engineer that would be able to maybe take the performance requirements and come up with something that was really completely novel, given that you're going to be building this on the scale of 1 billion units. The upfront development cost could be quite significant as long as you could produce it at unit cost very low. So this is just one design that we've come up with. And here we're using existing technology. We have sort of these wheels that operate orthogonal to the main wheels. So this is standard in a lot of mobile robot design. Again, I think there's probably more original techniques to develop a module like this, but this is something that is currently the best I've been able to find to date. In terms of network coordination, this is an area that I haven't worked on recently. I did work on a number of years ago. And here, the basic idea is that you have one distribution center, and then you have sort of a combination of multiple things happening at the same time. The first is at this local distribution center, you have loads that are being delivered locally to houses located near the distribution center. But then you have the distribution center itself as part of a larger network of other distribution centers. So in that case, you have loads that have items going to many different customers, all being transported together. And those then go on a vehicle from one distribution center to another distribution center. And just as an example of how you would actually think of actually coordinating something like this, you could have a mechanism where the loads themselves actually bid to be on the next truck leaving the facility. So essentially you have a sort of a competitive situation, and depending on the priority of the loads in terms of when they want to leave the distribution center, obviously a higher bid amount would more likely get them to leave the distribution center sooner than a low bid. So they could adjust the amount they send to coordinate their actual performance in the network. And what's interesting is this approach is also used by Kiva system that Amazon owns, Amazon Robotics. They're the little robots, basically are given sort of a pseudo currency. And then when they want to do something in the warehouse, they actually bid to do different elements. And that's the way that multiple robots are able to coordinate together effectively. And what's interesting about this problem then is you have a situation where you have different total bid amounts for all the different packages or loads that want to leave in one direction. They total to a certain amount. And then you have the vehicles themselves that are then given the opportunity to either accept or reject these different load bid amounts. So the vehicles themselves, depending on what their priorities are, can accept or reject different loads. And in terms of developing an overall protocol, for the operation of the vehicles themselves, the protocol would make it so that the priority for accepting loads is given based on the vehicle's expected arrival time at the DC. So the sooner it's going to be at the distribution center, that vehicle is given first choice as to whether or not they want to accept or reject a particular load. The idea there is to promote efficiency. So you don't have the vehicle accepting a load that's not going to be at the DC for quite a period of time. And then reneging, after reneging in terms of basically saying, I've changed my mind, then the vehicle itself cannot, again, accept the same load until all of the other vehicles have rejected it. So it puts a penalty associated with reneging on the load, so then you can't then quickly change your mind. The idea here is to not to have highly dynamic performance where bids are constantly changing over time, to make it so that vehicles give their best effort as to whether or not they want to accept or reject a load, and then knowing that if they later want to renege on it, it's going to be very costly for them. So it's not a cost-free thing. And here's just an example of the priority for accepting loads. In terms of here we have 4 different vehicles. 2 of them are located at a distribution center. So these would be given first and second choice. And then this would be given third and then fourth choice. And then for reneging, here we could have a situation where currently 2 vehicles accepted 2 different loads, and this is the amount of the load. But then we have a change of circumstance, and here the bid has increased from $50 to $200. So with that, the $200 would indicate that we probably want to have the closer vehicle be the one that actually carries this load. So how would you actually implement a change such that these could agree to actually switch with each other? Well, the way it could be implemented is to have a side agreement between the 2 different vehicles. And then with that side agreement, they both agree to accept the switch of the 2 bids. So with this configuration, we have a situation where the closer vehicle now is the one that is transporting the higher value load. In this picture, it shows that the 2 vehicles are very close to each other, so it doesn't seem like it would make a big difference. But in some situations, this vehicle might be, an hour away, this vehicle might be minutes away, so the difference could be substantial. Yes?
So is monetizing the protocol an attempt to solve logistics problems, or is it an attempt to put a free market on valuation of deliveries and actually?
Well, I think it's really meant to do both of that.
Okay.
So the idea of the protocol is to get as much of the benefit of a central control of the system. So, in terms of efficiency, it's meant to try to get the same efficiencies that you would get with a single company like UPS operating. And in some cases, we can show that you can't get exactly the same. So from a completely deterministic point of view, you can show that it's not quite as good. But I think there are benefits to having a more free market approach in that it allows you to scale the system. It doesn't require large central control. So it's really trying to get the best of both worlds.
I was just thinking that my linear algebra teacher, 30 years ago told me that, there's a solution to the matrix problem of, logistics, and it would just be a mathematical computation. You wouldn't have to be in negotiation. And this is a more dynamic algorithm, right?
Exactly, yeah. And also from a game theoretic point of view, there are situations that you can show that are optimal that are not reachable by these, and And again, this is still not a perfect solution because this can still be suboptimal. So it's really trying to do the best of it. But there's, in this case, no mathematical way of showing it. So what we do is basically just simulations, trying different scenarios. So it doesn't have, unfortunately, as nice a theoretical character as you would hope. And then for the container protocol, again, sort of the same idea to try to encourage efficiency in terms of the operation. So one element of that is load formation. And the previous example was a one-dimensional, but in reality it would be a two-dimensional problem. So the loads themselves are formed as part of a two-dimensional bid packing heuristic. So that's actually used to form the loads themselves. And then the allocation of the load bid, it's basically the vehicles portion of the load bid does not increase after acceptance. So once it agrees to accept the load, even if additional containers join the load, what do you do with that additional amount that they're willing to spend? In some sense, the vehicle's already agreed to transport it, so it doesn't need any more incentive. So the idea here is that the additional amount that the later containers then joined after the vehicle accepted the load, that amount of money then is divided with the containers that were the initial containers. So there's an incentive here for the containers to place a bid early when they want to be transported. Again, the idea is to promote efficiency so that containers don't wait. So if you think of sort of like sniping in eBay, we're trying to avoid situations where there's an advantage to wait until right near the end and then join the load. So here the idea is make your best bid early, and then if it ends up being accepted, then as other containers join the load, you might actually end up with a net benefit. You might actually be able to, instead of paying to be transported, actually make money depending on the amount of the later containers. So it's really like a continuous auction that will operate. And the key thing in terms of doing this, when I've had students working on this problem, from a computer science point of view, the key thing is having very efficient data structures that allow this to occur. So if you try to do it sort of just brute force, it's very inefficient, not really computationally feasible. So to make it work effectively, good data structures are necessary. This is just an example of load formation in terms of what are the different costs. Now, I won't go through this in detail. Let me just go through these quickly. And then this is an example of the type of architecture. And the DCs themselves could be some of the support for the services. For example, things like maintaining the different load bids. There would have to be some server-based storage of that. And then the agents could be used for both the container control and for the vehicle control. Again, this is a very similar architecture to the Kiva robot system. And this is an example of 2D load formation. And these are just 18 random containers. And for these containers, I've actually just generated random bid amounts. So both the dimensions of containers and the amount that they're bidding is just randomly generated. And in terms of the sortation, these containers are sorted in terms of decreasing length and then decreasing width. And these are the total areas. So with those 18 containers, the order sequence is determined based first on length, width, and then for ones that have the same length and width, then they're ordered in terms of their overall bid. The upper bound then represents the sum of the bids of all the containers, but because of packing considerations of 2 dimensions, it may not be feasible to pack all of the containers into a bin. So in this case, we have a total of 18 containers, and the upper bound then is a total of $14.09. So that's the most that we can do. But when we go to actually try to place them into an actual set of arrays, then when we do that, we end up with a situation like this, where this is the number of the different containers that are appearing in this load. And notice the yellow ones. I'll talk a little bit later about what the yellow indicates. So that's the final indication. What the yellow indicates are that among the 18 different loads, the loads 16 and 17 were actually able to be placed into this first load, but the amount that they bid on a bid per unit basis was actually less than another load. But another container was not able to become part of the load because it was of larger size. So it turned out that these two yellow containers were small enough that they were able to fit in this essentially empty space. And this is looking at what would be the total number of loads formed if we had a total of 38 different containers. And this would show you how it would sort of play out. Again, this is that same load that we saw before. These are the two that sort of got in for a lesser cost. These are also ones that got in for a lesser cost. And then these last three loads, they're basically all the larger size loads that got in based on how much they bid on a bid per unit area. So the reason I like this slide is it really indicates something that I don't think exists anywhere else in logistics, in terms of at least any proposed logistics systems. But here's one where you essentially have diseconomies of scale. And that's something that doesn't occur. Basically with logistics systems, you're always talking about trying to ship bigger sizes. You know, they're expanding the Panama Canal so that the ships can be bigger, carry more containers. So it's always scale economies that are the main focus. But this is a case, you know, just basically because of the geometry of bin packing, that it's actually more beneficial if you have to ship something, instead of putting 4 little items together as one big package, it's probably going to be cheaper, at least in this network, for you to break them apart as 4 separate containers and then ship them separately and then have them form at the end. You think of like the internet, they could all take different paths through the network and all the packets then form at the end to create whatever message. You know, same idea here in terms of it's actually cheaper to do that than any type of consolidation. So this is the one feature I really like about the network, that it really kind of runs against the grain of what you would normally think. So in terms of, as an industrial engineer, this is, I think, very interesting because it then also changes a lot of the dynamics of how you actually store and position inventory in a network. If you have diseconomies of scale, then essentially what you're saying is it's better to just order small quantities of an item. You don't, there's no advantage to ordering some bulk quantity and stocking up on something. So that would be a larger efficiency that would be promoted just outside of the operation of the network itself. And then finally, the last area is looking at sort of overall performance analysis of a network like this. And again, it doesn't actually exist, so you know, how would you actually address, you know, what could be the potential cost of this system? So what I did is I looked at, first probably one of the big uncertainties, what would be the actual cost for one of those modules that are part of each distribution center? And 2 estimates that I used, one was $100 per module, and another was $50 per module. Again, 50 is maybe a little bit aggressive in terms of price, but again, if you're producing 2.5 billion, 100, maybe not. Actually, I had Charlie, what was your estimate of these modules? I think it was like, you thought it was like under $50, so I was really happy when you kind of looked at the module design. So he was one of the first people that kind of looked at it and came up with an estimate below $50 per module. So again, taking those 2 numbers, and then in terms of the time for loading and unloading, 5 and 10 minutes. And then this is the utilization of the distribution center, 60 or 80% utilized. Again, in practice, we don't exactly know what would happen. And then finally, in terms of household demand, here I broke it down in terms of how many trips per week. So aggressive would be 4 trips per week that you would order something. So it's definitely not every day, but 4 times a week. Conservative would be maybe twice a week that you have deliveries. And then finally, the last would be how many modules would be occupied on each of those trips. So when you order something, would you on average be ordering 10 units or 20 units? So these are really very small utilizations of the vehicle. So you're not really occupying the entire vehicle by any stretch of the imagination. So with those numbers, then going through the analysis, it worked out that the range of costs that we got, the low was $1.45 and the high was about $5. So if you remember, the goal of the research originally was to make the cost of this equal to what you would maybe tip the pizza delivery guy. So if you're generous, maybe $5, maybe $2 if you're not. So it kind of falls within that range. But again, this is all based on a lot of hypotheticals at this point. So this is something that is not anything currently going to happen immediately. but it's really more of a look at when you actually build out the network. So this is the Starship. This is a company that's doing pilot studies this year. And what they're developing is a small little robot that operates on the sidewalk. And the idea here is very similar to the research I'm doing, in that this vehicle would actually come to your house, and that inside of it, you'd have just about a cubic foot of packages that could be in that robot. And they're looking at trying to probably they're doing pilots this year, so they're really probably trying to have something available within the next year or two. And in terms of technology, their focus is not on having an entire logistics network to support this. Their focus is just on this last mile technology of delivery. So in some sense, what I have been talking about is more something that, beyond this, how would you build it out such that these type of vehicles, together with the larger driverless vehicles, could operate very efficiently and not require any kind of high-cost back-end. And I think they're looking at things like robots for loading the vehicles and things like that, which is fine, I think, for small scale. But as you scale it up, I think it's preferable to have more specialized technology. So hence the idea of the distribution centers with the modules and stuff that allow you to really take advantage of the unique characteristics of this type of last mile delivery. Any questions? Yes? Which part of Amazon? The drone deliveries or? Yeah, exactly. So this is in that same, the idea is would be if you wanted to do it sort of fully automated, to allow that. So I think the difference is, for there it's a couple dollars, but the amount that you get here is the size of the vehicle itself. You could have, essentially a week's worth of product delivered for maybe $2 to $3 or $4. And with Amazon, you're talking a couple dollars for each delivery. So the focus is a little bit different. Yeah. Excuse me? Yeah. Well, I think with Prime, though, what I find is you're paying for it in the cost of the product. So it's, the delivery cost is kind of pretty well hidden, so it doesn't really change the logistics of it. I mean, but essentially Amazon will be probably going to something like I'm talking about. It's just a matter of more of an evolution. I mean, they're looking at autonomous vehicles and driverless vehicles, and they're building ever smaller distribution centers. So in some sense, it's it's kind of a natural evolution towards this. So it's not really an either or. I mean, I view this as just a sort of the logistics network component of this last mile delivery. So my real focus is more just on how do you operate the distribution centers efficiently to support that. And I think it's entirely compatible with Amazon. Yes?
So, with the efficiency of your distribution system, you feel it's going to open any economic debates in terms of a lot of practices that were done with the robot seats were either unethical in terms of what we do in the real market or illegal?
What aspect of it?
In terms of like side agreements, things like that, because even if it's not legal, more so unethical, so do you feel with the efficiency that's going to open up debates whereby we should implement it in our own system and how we can regulate business?
Well, I think it might be the place, like if you have like different vehicles. I think one of the goals of developing a protocol is to make it so that it's okay to make side agreements, but those side agreements can't disadvantage anybody else. It makes the system more efficient without making it inefficient for anybody else. That's one of the real, I think, interesting from a research point of view, is to incorporate that. But that's actually deliberately there, to say that you can do side agreements, but to make the protocol such that it supports it without allowing you to disadvantage anybody else. And some of the elements of that protocol are essentially there to eliminate, hopefully, that possibility. And one of the things I do is, in terms of this protocol, is I actually have the students in my class manually implement it. And there they have every incentive to try to sort of break the protocol, to do better than they should be doing. So that's one way of kind of testing it, seeing can they make side agreements with each other and do better than they should. That shows me then that there's something wrong with the protocol. You could also simulate it on a computer. The problem is that if I simulate it, it's just me thinking about it. But when I have like 30 or 40 students, all with different agendas and different ideas, that's, I think, a much better test of it. So that's something I have done over the years. And again, it's not a complete process, but that's actually a very strong motivation to develop this, is to really make it possible so that it's not something that is, because I think anybody using this would not become very interesting for people using it if people thought that it was kind of biased. For them making a bid, they were somehow getting undercut by others that were manipulating the system. I think you feel like that when you use eBay or something. If you're doing an auction, if you don't feel it's a fair process, you're not going to be utilizing it. Yes.
So I saw on one of your slides you're utilizing the warehouse was between 60 and 80%. Is that what you said?
Yes.
So have you considered queuing theory? So I don't know if you're familiar with that, or
Yes.
it's like having 100% of cars on the freeway.
Yeah.
It's quick and easy to get bottlenecks.
Yes.
And I wonder if would you consider it different because it's robots and not humans?
What was interesting about that design of a distribution center, a lot of current material handling systems, it's either working fine or once it reaches capacity, it kind of stops working. So it's like very like a binary state. But this type of module design, it kind of is you kind of congest very slowly. But once you go beyond about probably 80–85%, then it starts to get longer and longer. So what happens is it takes longer to get through. So just like driving a car in a city, everything kind of slows down. So usually in most design, you don't want to go above 80 or 85%. It's usually an upper limit in terms of
I
size.
heard that 50 is more reasonable.
Yeah, but depending on what some systems even 50% possible. Usually the rule of thumb is about 80% for most systems. And once you get beyond 80, then things start going up exponentially in terms of how long you can be waiting.
I'm interested in what you think the greatest inhibitor to implementing a system like this would be.
I think, well, the idea of the driverless,
Okay, infrastructure or autonomy of vehicles.
Yeah, well, one of the features of this system that I didn't really mention, but I think is maybe potentially of interest, is that these vehicles, first is deliveries don't have to be done if it's bad weather. So if it's rain, ice, snow, things that would maybe inhibit current driverless technology, this could be sort of a first use case for driverless. Because it's not like a person on board. You don't have to go out if you don't want to. So it's entirely, unless you're delivering maybe life critical elements. But,
Or pizza, right?
Pizza, yeah, you have to have your pizza. But so that element, but also the travel speed, because these local distribution centers are typically just a mile or two from your home. So the travel speed we're talking about is about 15 miles an hour. And then once you reach a residential area, like a residential street, you can travel at 5 miles an hour. So in terms of the collision avoidance technology, it's something a person on board would probably wouldn't want to sit in a vehicle going 5 miles an hour. So in terms of as a test bed for first deployment of driverless, I think this would be ideal. But I guess I'm biased because that's what I'm interested in. But before you actually have people on board, it would seem like this would be a good first case. But I guess the trade-off is that these would be operating in home environments. In terms of neighborhoods with a lot of there wouldn't be restricted areas. So you might have kids out playing and stuff. So. But I think it's having a driverless vehicle going faster with a person on board is probably a longer-term prospect. So this could be done much sooner than that.
I see community standards for infrastructure as being an inhibitor because there's all variation of what residences have sidewalks, not have sidewalks, have access, would be street access versus, pedestrian access.
This is interesting, is that what I'm thinking, what I envision is basically a driverless vehicle that would operate on the streets and then would come like up your driveway, and that's where you would actually unload.
Yeah,
And the Starship technology, it's basically operates just on sidewalks. It's too small to go on the street.
Well, and 5 miles an hour is
Yeah.
going to cause the same problem as
Yeah.
bicycles and pedestrians do.
And what's interesting is with the Starship, when I actually was talking to the people at Starship, and one of the, because they saw my research and they were kind of interested in comparing notes. And one of the things that I commented to them is I just didn't think in the United States, I guess maybe I'm biased living in Cary or something, that we don't have a lot of sidewalks and they're really not easy to access one point to another. And that was sort of my take in that I think you're kind of really limiting yourself. And what they said is that they did a mechanical Turk, Amazon mechanical Turk experiment like a year ago. And And they had people randomly look at images throughout the United States, and they had estimated that there was 80% coverage of sidewalk for all the residents in the United States. I personally don't believe that, but that's what they said. So.
Some locales it's mandatory and others
Yeah,
it's not.
so, and I can't say that I've done what they've done. They've actually looked, had experimented. So it could just be my bias that I don't see that. But I thought it was a great use of mechanical turk. I thought that was quite clever that they had actually researched that. But you can tell, obviously, that a lot of people have complained. And does anybody guess what the second issue that comes up all the time with this? Even my students, when I present this to class, that's the first thing they think about.
Yep.
That exactly, what takes somebody more. So when I was talking to the guy who developed it, he was actually the guy who developed Skype. And so he's focusing a lot on the communications technologies for security. So he talked about all the different cameras and all the different mechanisms that are on board this vehicle so that if somebody tries to steal it, essentially there's somebody's there saying, don't think of taking, try to scare somebody away, and then if they take it, then to be able to track the vehicle. So a lot of their technology and development is that issue.
I'm already working on this opaque net for Android drones.
So,
when they
so I find it amazing that that's everybody's first thought. I mean, if you ask a class of 20, 30 students, 3/4 of them, that's the first thing they think about. So I don't know if that says something about their I guess my first thought was the lack of sidewalks, so I guess I wasn't thinking that way. But anyway, I think it's really been interesting, especially what I found also is that back when I started this, drones didn't even exist. And driverless was something that wasn't even quite on the horizon yet. And what's funny is now most of the focus is on drones. And really Starship is one of the few that's looking at sort of the ground-based component of delivery. But I guess my contention is that the economics are such that I don't think you can have everything delivered by drone. I think it's good for high-value critical items. But I think the proverbial gallon of milk, the economics of ground delivery, I think are preferable.
Did the Department of Defense or et al., haven't they had ground vehicle autonomous navigation on unrestricted terrain, and they ran into tremendous difficulties. The robotics problems in that is even more difficult than underwater and aviation.
Yeah, trying to extract yourself in different.
Yeah, I mean, going through a mud puddle and you get stuck, right? And now you have to extricate yourself.
What's interesting though is Google actually came out of the DARPA challenge. So I guess it was back in 2008 was the last time they competed. And, they had all these problems. It looked like it was 20 years away from, and then they kind of went black for up until was it 2011, I think. They presented.
Was it the desert drought?
I think it was the desert one.
Oh, really?
So they went, and it was amazing the progress they made in that 2 or 3 year period. When they then presented in 2011 at the IRIS conference in San Francisco. That was when they first unveiled the Google driverless vehicle. And it was just amazing the progress, because I'd been tracking the technology, and I was really just astounded at the progress they made in 3 years. It was much faster than I would have thought. Any other questions? Thank you very much then.